You guys ready to start? That's the spirit. I got a few, I hope, simple clicker questions about last lecture's material, so whip those out and we'll see where we stand. I'll give you time to log in and whatnot. So we talked about atoms made up of protons, electrons, and neutrons. Try to gauge where you're at. 10, 9, 8, nobody's squirming, that's good. 7, 6, 5, 4, 3, 2, 1. Huzzah! Right. This is, I really wanted to ask this to re-emphasize. A lot of people think when something's charged, it only has that charge. But no. Everything has charges. They're just in balance most of the time, neutral. So if it has 22 protons, it has 22 electrons. It's neutral. All right, ask you one about Coulomb's law, which tells us the force. Hopefully only slightly trickier. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh. Okay, you all think it increases, B or D? So it either increases all the time or only if they're opposite charges. I'm going to let you talk to your neighbor on this one. Obviously, some of you think there's a condition where it might matter. I know some of you don't sit next to anybody, but I'll feel bad if you miss it 2 times in a row and not benefit from your neighbor's wisdom. Yeah.
Are the forces attracting or repelling?
That's kind of what this question's getting at. Does the force only work for attraction or repulsion? Because the trick here is, you know there's 2 types of charges. I'll help you out. Like charges do what? Repel. Opposites attract. Yeah, but there's forces in both cases, correct? Does Coulomb's law apply to both? Or only one or the other? That's what this is asking. That Coulomb's law tells you the force between charges, but does it matter what the charges are? So re-vote. We'll see if we've shifted anybody's minds, and we'll discuss it more. 10, 9, 8, 7, 6, 5, 4, 3, 2, somebody's not playing, 1, oh well. Oh, a big shift. Most of you think it doesn't matter now. Good. Say you taught yourselves. So true, if you had a proton and an electron, they're going to attract. The force the proton exerts on the electron is determined by Coulomb's law. And how does that magnitude of force compare to the force the electron exerts on the proton? So in other words, the force this exerts on this one versus the force this one exerts on this one. They're the same. That's what Coulomb's law gives. I'll write it on the board again in a second. So it gives the force for both charges for attraction. Now let's make them both protons. Same distance away even. What are they going to do? Want to repel. But how much force? Same force. This one will feel the same force this one feels, but it'll actually be the same force the electron felt too. It's just one, the force is for attraction, and one, the force is for repulsion. Because they have the same magnitude of charge. And if they're the same distance apart, it'll be the same force this way, this way, this way, or this way. While we're on it, let me just write Coulomb's law back up here. Electrostatic. Well, there's a constant of proportionality. For those of you who want to know, it's Boltzmann's constant. A really big number. One charge times a second charge, the distance they are apart, squared. So it involves both charges. The amount of charge determines the force. If we took 5 protons and an electron, the force will be 5 times as big between them. But it'll still be the same on each one. Even though the electron's all by himself and puny, it'll still feel the same force as the 5 protons do. That's the diesel truck and the mosquito, Newton's third law. But it doesn't care if they're positive or negative. That just determines which way the force is going to go, try to attract or repel. So, back to this question. If the distance, they get closer together, the force will increase, whether it's attraction or repulsion. All right, how about a charged balloon and the door? How do the charges interact? And that is accurate. When you rub a balloon on your hair, the balloon tends to become negatively charged. What's it do to your hair? Yeah, it leaves it net positive. And whatever electrons got transferred to the balloon are now deficit from your hair. So they're charged equally, just oppositely. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Well, there's obviously a big consensus there. Right. What? Nah, never mind. I'll ask it this way. What if the balloon were positively charged? Would it still attract to the door? Or would it be repelled? It'd be attracted, right. It's just because it would shift the charges in the door oppositely, though. It'd still polarize them. It would attract the electrons then, instead of the protons.
Did you explain what happens to the balloon? I mean, if it, did you say it was next?
That was the last one, so go ahead and I'll get the lights on. And I'll draw a picture. Let's see, we got a balloon in the door. So if this is there's more negatives than positives, so it's negative. This has positive and negatives. But if there's more negatives here, what's it do to the negatives in the door? You just answered it. It repels them. So they end up crudely more on this side. And the positive charges are attracted to that negative charge of the balloon. So they're shifted more that way. This is called polarizing the thing. We'd say the door is currently polarized. It's like temporarily charging it. While I'm at it, What's the net charge of the door? Good. It's still neutral. Well, these negative charges attract to the positive, so when you bring it near the door, you saw the balloon will stay put. It's held on the door by Coulomb's law, the force between the charges. Does that help? This would just reverse if this were net positive. As drawn, it hasn't changed yet. When you touch it, you bring the balloon right next to it. This is an insulator. This is an insulator. So as soon as they make contact, charge won't transfer just like whew and go into like a metal and spread out. However, there is an excess of electrons here, and so some of those can move to the door right, but locally. They're stuck there. They're not free to spread around. So, right there on that spot, it'll be a little more negative, yes. If this were my finger near the balloon, until we touch, my finger would get polarized. But as soon as I touch the balloon, those negative charges on here now have a conductive path, and they'll come off through me. And I can actually, yeah. You wouldn't completely discharge this, though. Why? If I touched it with a conductor, how come this wouldn't completely discharge, become neutral again?
Because when the negative, or I guess when the electrons transfer into your finger, the negative will start repelling each other.
Oh, that's logical. See, you're thinking like a scientist. That's good. I hope you guys have learned to reason better throughout this semester. We're almost done. Are you sad? Just a little? Happy too, I know. But I want you to be better citizens when you're out there too. So when somebody presents you with something, you can, wait a second, let me reason it through. Don't always take it at face value. Scientists are always asking questions. But some of these electrons will move to my hand. Yeah, but since I'm a conductor, they'll actually go into the ground if I'm touching ground. But which ones are free to move? Only the ones right where I touched, because I grabbed them. An electron over here isn't going to flow through the balloon, because it's an insulator. I would have to touch it a lot to get most of the charge off. If this were a metal ball that was charged negatively, and I touched it, then all the excess would come to my finger, because they can get there, and they'll leave. And that would completely discharge it and make it neutral. Like the electroscope when I touch it. So remember the difference between insulators and conductors when you're doing this too.
What is like a shock?
That's a shock. A shock is a transfer of charge. And if it's enough charge flowing through you, it can hurt or kill. Yeah, chapter 22 again is electrostatics, where we're not moving the charges around much. Or at least they're not flowing. Electricity you're used to dealing with, circuits, plugging things in, that's the flow of charge. And when it goes through you like that, you're creating a little circuit. That's a shock. You've done it too. You take your shoes off, or you're scuffing, you're on a carpet, and you touch the doorknob, or you get out of your car, right? You slide. When you rub things together, charges separate. Well, you've probably just created an excess of charge on yourself. Either an excess of electrons or a deficit of electrons, depending on the materials. You're charged. Then you get out and you touch the door, right? It's metal. And so that the charges rebalance by flowing. That's a shock. And if there's gas fumes, vapor, really thick, confined around your car, and you make a little spark, yeah, there have been fires at gas pumps. You've seen those signs where they tell you not to use cell phones near a gas pump? That's one reason. They have changing electric fields? But it's more dangerous I don't know, I don't have data for this. But it's more common for people to put the gas in their car, fumes are coming now, and get back in their car. It's like, rub, 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 right? You're sliding around. They're getting charged up, so they get back out. What do? They walk around to the gas pump. They touch it. Shock! Right near the vapor. Not a smart idea. So, I won't say you should. I choose never to get back in my car because when I get back out, or at least when I get back out, right there on the opposite side, I shock myself, discharge myself before I go over to the gas handle. I did read statistics about this, though. Don't take it the wrong way, but women tend to get back in the car more often than men. And so this has happened more with girls at the pump. If there's any validity to that. But anyway, something to chew on when you're out there in the real world. Here's an example you can do at home. We'll take some tape. I just separated it from the roll. So do you expect this to be charged? Let's find out. Whoop. Yep. Because it attracts to my finger. Just like this. It's polarizing the charges in me. But it's still charged even though it touched my finger because not all the charge on the tape it's an insulator, can flow off of it. So it's charged. I don't know if it's charged positive or negative. But if I do a second one, this should be charged also, right? Yep. Should have made it a little longer. Oh well. This should be charged the same way as this one because they came off the roll the same way, right? So again, I don't know if they're positive or negative, but they're both charged the same. So what do you expect when you bring them together? Look at that. It's not some inherent stickiness force either, you know. Works for any side. Yeah, they're repelling each other because they're charged. They still track to me. Then, here's the fun part. You can put it down, piggyback this one, touch it. Now what I'm doing is getting the charge off. I'm trying to neutralize it so it doesn't have excess charge anymore. Let's see. Pretty good. Well, now I'm going to separate these two. One side should take more electrons than the other. So they should be opposite now, right? Do they attract to me? Yep. Does this one attract to me? Yep. So they're both charged, but opposite. Whee! Well, the first time they came off the roll, same way, so they got charged the same. This time, though, I piggybacked them. You know, one side's sticky, one side isn't. So one side has a greater affinity for electrons than the other. So I just piggybacked them and ripped them apart. So now one's more negative than the other. And they attract. Kind of fun. And that's Coulomb's law at work. Well, I'll admit, I'm a nerd. If you didn't know, given the weight of these, you know, gravity's pulling down. There's a Coulomb force attracting over sideways, right? Well, given the weight of these and that distance, the angle apart, I can calculate this force. And this is a constant. I know how far apart they spread. I know the charge of electrons. So I can estimate how many extra electrons I put on the tape. And it works. All right. Electric fields. Charges have electric fields. It's kind of an ambiguous term for some folks. I'm going to try to make it simple. You're used to gravitational fields. We just usually don't call it a gravitational field. We just call it gravity. So that's going to be our analogy, because an electric field's like that for charges, where an electric field does to charges what a gravitational field does to masses. So the equivalent is it's more like, it's kind of like the charge. So if you have a charge, picture a proton. there's an electric field around it, like this imaginary force field. Just like this mass has a gravitational field around it. It gravitationally attracts things to it. It's like the Earth. The Earth has a gravitational field around it. That probably makes more sense to you. We're in it, so what happens when we're in it? It pulls it to us. Gravity force is always attractive, where the Coulombic force can be attractive or repulsive. So this has an electric field around it. They give it a direction. Gravity is always pulling. Positives go away, like this. And if you had a negative charge, it would come towards it. The way I remember this is they did convention, and say you took an infinitely small positive test charge and you stuck it in this electric field, which way would it go? Yeah, away, because likes repel. That's the direction of the electric field. So if you put a little test charge right there, it's going to feel a force in that direction. So that's the direction of the electric field. This electric field exerts forces on charges, just like the gravitational field exerts a force on this, pulling it down in the direction of the field. Gravity's down. Likewise over here, it would be attracted. So if you forget this direction, just think of a positive test charge and which way it would go. If you had these next to each other, a proton and an electron, you can see there's an electric field line that would go right to it. And this one would kind of be curved. It would start repelling from the positive and end up at the negative. And you can get pretty pictures. Whee! You get the idea. You can draw these electric field lines. What's nice about that? It gives you a kind of a heads up with like a contour map. Any of you hikers? We're in Utah. Probably some of you got to be hikers. Where the lines are close together, what does that tell you on a hiking map? It's steeper. That means there's a bigger change for that given distance. Same thing here. If they're closer there, it's steeper. What's steeper? The electric field. The electric field's higher where these field lines are closer together because there's a bigger change from here to here than there is from, say, here to here. It's not changing as much. So the electric field isn't as strong out here as it is right there or right there. And you'd feel that influence. So, our equation to guide our thinking is this. The electric field one way to think of it is force per charge. A charge feels this force, that's the electric field. For your analogy, if we had a force, this is the electric field, the Coulombic force. If this is the gravitational field, and you put a mass in the gravitational field, what does that mass do? Here's review for the final. You put a mass in a gravitational field, exert a force on a mass. You push something. You push an object. What's it do? It accelerates. Which law is that? Newton's second law. Good, Ron. Yeah. See, I just rearranged it, F equals ma. That's the gravitational force. So another way to think of this is, well, we talked about something's got inertia, it doesn't want to move. To change its motion, accelerate it, you got to push on it. You got to exert a force on it. Kind of flip it around. You put something in a gravitational field. We've got weight, right? We're in this gravitational field. You put a mass in it, what's it going to do? It's going to feel a force and start moving. That's how this works. We can rearrange this guy to See how that's the same thing? You put a charge in an electric field, it's going to feel a force and start moving. In which direction? Well, that's what the field lines tell us, in attraction and repulsion. So this is kind of like Newton's second law for charges. Hopefully that'll help you. So remember one of these versions. Energy. We did a lot of energy. These things are blocking everything. Stay. All right. With gravity, we had gravitational potential energy. Remember what it was? mgh. Basically, you took that force and moved it a distance. What's force times distance? Good job. Work. So in order to give something gravitational potential energy, this mass, I have to exert a force on it to accelerate it, change its motion, and raise it up, move it a distance, force times distance. So I just did work on this ball. Energy is conserved. Where's that energy now? In the form of gravitational potential energy. It has the potential to do work now if I let go. Why will it move when I let go? Because it's in a gravitational field and that exerts a force on it. It makes it move. So here's the force. I had to at least exert its weight upwards and moved it up. Well, the same thing's true for electric potential energy. I mean, these charges can have energy. And it's just like lifting a charge up. But what are you moving it against? The electric field. This we move against the gravitational field. Gravity is trying to pull it down. So if we swim upstream, you have to put energy into the system and do work. The higher it is, the more gravitational potential energy we say it has. So now think of this as a proton. And the electric field is down. Will be consistent. They go away from positives. So it's kind of like, it's kind of like you have a whole bunch of positives up here and a whole bunch of negatives. That's the electric field. Which way does a proton want to go? Down. So, in order to move it from here to here, it's going to take energy and work. And by doing so, it now has more electric potential energy. Because if I let go of it, it will accelerate down. That's what the electric field does. So, mgh. The m is q. We're dealing with charges. What's doing the accelerating? The electric field. And how far is it moving? A distance. So, that's your friend also. You move a charge in an electric field a certain distance, it has gained that much electric potential energy. That's how we can store charges, our batteries, Batteries and capacitors, somebody had to separate the charges. The charge is down here and happy. Somebody had to go, whoop. Okay, now it's ready to do work. It has potential energy. And you use up the battery. Then you have to recharge it, right? That's the idea. And this is how you can figure it out. Now, the part that confuses more folks. Hopefully that's straightforward since a third of you are sleeping. Kind of like with fluids, instead of dealing with all the individual little particles, it was easier to, and adding up all the forces, it was easier to deal with pressure. Let's just deal with them in bulk. We kind of do a similar thing with charges. There's a whole lot of charges. We don't want to pinpoint every one. The electric field is force per charge. Per charge. But that would get tedious. Can't we just say how much energy something has? Sure. If we know the total charge. So they use this other term, which you're probably the most familiar with. And it is, let me, for clarity, because whoever chose these terms, this is electric potential energy. The new term is electric potential. Often referred to as voltage. They're the same thing. And what it is, it's that electric potential energy per charge. So instead of having to deal with the individual charges, let's just do it per charge. So you can have a whole bunch. And that's what electric potential is. And the author uses these interchangeably, electric potential and voltage. So when you hear something like a 9-volt battery, voltage is measured in volts. That's the electric potential. That gives you an idea of how much energy per charge the battery stores or can give to charges. This is in joules, and charge is measured in coulombs. Like Coulomb's law. This comes in handy because depending on what charges you have or how much charge you have, you can always say the voltage, and it's the same quite often, even though the energy can be different. What was our example before? Oh yeah. Remember temperature? It was a measure of the average translational kinetic energy per particle you're dealing with. Remember my example, or the book's example, of a sparkler? Sparks. I came out here and made sparks. Are the sparks hot? Yeah, their temperature is really high. But it doesn't really hurt when it hits you. Do you remember why? Yeah, there wasn't much to it. There weren't that many particles. There wasn't much mass. The analogy is similar here. Something can have a really high voltage. That means it has a lot of energy per charge. Temperature. They were hot. It had a lot of average translational kinetic energy per particle. Each particle had a lot, but there weren't that many particles. So if you have something high voltage, it's not always dangerous. If you don't have very many charges, see if Q is small, do you see how you can get a big voltage per charge? You still might not have a lot of energy there. A Graaff generator, have you guys seen these before? This can get up to hundreds of thousands of volts. That's a high voltage. It has a lot of energy per charge. But it's not dangerous because it doesn't move around many charges. The charge is small. So there isn't much energy per charge. No. There's a lot of energy per charge. There just aren't a lot of charges. So overall, it doesn't have enough energy to kill me. That's why people touch these. Shall we do it? Somebody like to try it? You come up here and put your hand on it and we let charge go to you. It'd be fun with somebody with longer hair. Maybe we can see it stand up and repel. Any takers? Do you want to, Brooke? I mean, Lee? You want to? Sure. Okay. We'll have you stand on an insulating stool because we want the charge to stay on you and not go off the ground. So you can just put your hand on here. And you're safe just if you don't let go and don't step down.
Okay.
I'll get it going. It takes a minute. We'll talk some more. You'll feel it immediately.
Look at my eyebrows.
Yeah. So this is charging up. Now I'll talk about that more after I turn it off and don't have to yell as much. Yeah, it's working. So let's say it charges up negatively. Those charges can flow onto her because she's a conductor. They can flow under her hair. Negative charges don't like each other. So they want to repel. And the easiest way to do that is to make your hair stand up and spread apart. Give your hair a good shake. Where's my mirror? Works like a charm. Now, those are charges. They're feeling the electric field. And they're trying to be repelled. Her hair is essentially forming the electric field pattern. You see it? It's like you can think of her head as a big charge. And the field lines radiate out from it. All right, let me turn this. Don't let go. And see, charge stays on her because it has nowhere to go, no path. She's insulated from the ground. You can let go now. It's still standing up. You can put it down though. I'm actually stalling too because you have an excess of charge. What do you think will happen when you touch the ground? A little bit. Not as bad with it because it dissipates through the moisture in the air. There is a conductive path through the humidity. You're safe enough now to step down. You will feel a little thing, but you feel that? Did you see her hair go down too when she touched? Charge left her hair. Thank you for doing that. And I know if you're worried about what you look like here, you can. Okay. Let's do some pie plates. Is the Coulomb force strong enough to overcome the weight of pie plates? You betcha. How about packing peanuts? It's just so it doesn't fall off. Ready? Woo! They followed the electric field lines. All right, now this is connected to ground back here. So this will charge up, have an excess of charge. And if I separate, make a gap, you can hear it if you can't all see it. Charge builds up. Once the electric field's big enough because there's enough charge, whammo! It can ionize the air, break it down, make it conductive. Pause while I talk. Makes the air conductive, so the excess charge has a path now to ground and it leaves. Then it builds back up, whammo! Builds back up, whammo! This is lightning. When updrafts, all about buoyancy and density, they go up and they rub against ice crystals in the clouds. Charges separate. Typically, the positive charges go up with the updraft, leaving negative at the bottom of a cloud. You've polarized a cloud. And if the bottom of the cloud's negative, it's closer to the ground than the top of the cloud. So what's the ground do? Cloud, positive on the top, negative at the bottom, comes over a piece of ground. It's like bringing the charged balloon near something, the door. It gets polarized. See, negatives are on the bottom. So yeah, it makes the ground net positive on the surface because it's polarized it. And if that charge difference builds up enough, there's a big enough electric field that will accelerate the charges and whoosh, it'll jump to neutralize it. That's a lightning bolt. And I always like doing this demonstration, though, to teach people about lightning rods. Lightning rods are just sharp points. Benjamin Franklin was a genius. One of those simple inventions. What's the purpose of a lightning rod? To gather lightning? Attract lightning? Yeah. Who agrees? Okay, because that's like 95% of everybody I ask, that's what they say. Lightning rods are to attract lightning. And that's why I teach this, because that's wrong. If lightning strikes, it's more likely to strike your lightning rod. So they attach a wire, like you put it on your house, right? And there's a wire here to ground. So if lightning strikes, instead of going through the circuitry of your home and frying everything, or you, it'll guide it directly an easy path to ground to keep you safer. But the real purpose of a lightning rod is to do this. Let's see how far it can jump, first of all. Out there-ish. All right. Let's put a lightning rod on your house. Hey, no lightning. The real purpose of a lightning rod is to keep lightning from striking your house in the first place. So what's happening? What's it doing? Why isn't it jumping and striking? Why does it jump in the first place? The only time it would jump is in what conditions? What's that? A difference. A big enough difference. Yeah. This is always building up charge, as we saw with your hair. And if it builds up big enough, so there's a big enough difference, the electric field's great enough, it'll jump. So, since it's not jumping, there must not be as much charge built up. That's correct. The electric field is weaker here. And so it's less likely to strike your home. Sharp little points in corners and edges have really high electric fields right at the point. Remember I told you the spacing between electric field lines tells you about the electric field, where they're closer together. So if you got a cloud up here, right? Positives at the top, negatives at the bottom, and you got ground below, some skyline. Woo. You get the idea. It's going to polarize it and have bring the positives. You get the idea. Where's it likely to strike first? Tall things, because the distance is shorter. It's closer. Yeah. But right here, at the little sharp point, this might go an electric field line. This might go, this could even go positives to negative. That's the direction. Away from positives towards negatives. This one can go. But what about one that's, where's it going to go? Here. 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 It's going to see that first. Something down here might be safe. This one, one of the heads up here maybe can get through. Sharp points bring the field lines together and make a really high electric field. The result is, what I really like you to remember, is sharp points and little edges that are really sharply curved allow charge to bleed off. Because they're going to move where the electric field's higher. They feel accelerated more there. And so all this excess charge that builds up on your house or the Van de Graaff dome has a path away. It's ionized the air because of that high electric field, and they bleed off. This never builds up to a high enough charge, so the difference isn't big enough and it doesn't spark. Here's another way to show that. Instead of using Lee and torturing her, I'll use the fur here. I won't even get shocked. That shocked me. But if I bring this near it, I don't get shocked. As opposed to... Ow. Sharp points have a high electric field because the field lines are close. So it ionizes the air, which makes it conductive, and any excess charge in the vicinity can escape into the air. And so it can just be in the region. And as I get it closer, more and more charge bleeds off, and by the time I touch it, it doesn't shock me, as opposed to like when I did this. I could feel that. I can show it a different way. Let's take the charge off the dome, and I'm going to run it into this little electrostatic whirl, I call it. I guess put it over here. It's free to spin either direction, but it's got sharp points on the ends. So if charge transfers over to it, where's the charge going to get shot off? At the points. So if the points are shooting charges away from them, what are the charges going to do back to the point? Newton's third law. It's action-reaction. Watch it. And which way is it rotating? Away from the point. So the point shoots charge away, and it recoils. And me, just being in the vicinity of this, charge is kind of through the air, leaked onto me. I could feel some sparks between me and the metal back here. But that's like the lightning rod effect. They try to power spaceships. You've heard of ion propulsion? Ions, you know what an ion is now. A charged atom. And if you can shoot them off, you can propel yourself. There's a high electric field. It's like a fancy gun. Well, these electric fields, we finally made it back to this one. Go ahead, Tom. That is not how electric cars work. They run off of batteries instead of gas. They both store energy. Gasoline has chemical potential energy. Batteries have electric potential energy because somebody already did the work to charge the battery up and separate the materials. So now they want to go back and they release that electric potential energy and turn it into kinetic motion so our car can go. What I think is cool, though, is you can shield from electric fields. You can't from gravitational fields. You know, you're still attracted down whether you're hidden in a box or not. Electric fields, though, you can. So back to this. What did we get today? So you remember radio waves, electromagnetic radiation. They have an oscillating electric field, right? Moving charges. They can make charges move. Here comes an electric field. The antenna sees it. That electric field makes the charges in the metal conductor move and oscillate because they're free to. That creates a current. Then you tune it by some circuitry to find resonance so that it will oscillate at the same frequency of the station you want. That's how you can pick which station to listen to. But it's all because here comes an electric field getting to the antenna. What if the electric field can't get to the antenna? This is a conductive cage. The electric field hits it. It makes the charges, the electrons in this, move around. But it's effectively shielded any of that electric field from getting inside to the antenna. Now they can. Come on. If it's completely surrounded by a conductor, it can act as a cage. You can shield from those electric fields. So inside a conductor, there's no electric field, you know. So there's people that walk around with aluminum foil hats and everybody thinks they're crazy because they don't want the aliens probing their brain. There is some truth to it. If they're probing with electromagnetic radiation, the electric field couldn't get in. They're essentially shielding themselves from being probed. So yeah, they're still crazy, but there's some truth to it. How many hate losing reception on your mobile devices? You go into an elevator or my office, which I'm below everything in the basement with no windows. The waves don't get in. 50% of people's phones don't work back here because the electric field has been being shielded from penetrating into my area. So, time's up. Electric field, like gravitational field, will accelerate charges like the gravitational field will accelerate masses. Both can gain energy depending on if you go against the field. You release it, you can release that energy. We're going to start releasing and doing circuits and moving these charges around more next time. And I'll finish the ones I didn't get to, but they're just more of the same. So, any questions? All right, have a good day.